Well, we are nearing the end of our Cisco foundations, or more specifically, network foundations, as in how devices communicate on the network today. At this point, I'm going to say we are good at layer 2. We understand the data link layer. We understand MAC addresses, physical addresses burned into the network cards of the different devices, and how that interacts with layer 3, the IP layer, and IP addressing basics, fundamental, and communication, how the ARP protocol resolves. I mean, all of that stuff we've talked about in the previous nuggets. So now I'm going to move up to layer 4, TCP and UDP, the last really network relevant layer that we're going to focus on in here. We're going to see where these two fit into this puzzle of network communication, and it's going to bring up a whole bunch of port numbers. So I'll give you some common ones that you'll want to know, not only for certification purposes, if that's your direction, but also, I mean, you use these all the time in the real world. And then we'll complete the end-to-end communication story, where we start looking at, from this host to this host, what are all the factors that go into making packets transmit successfully across the wire. Oh my goodness, I totally forgot to mention that we're going to start learning about Wireshark in this nugget, which it's awesome. You're going to really see a lot. That's what this little icon is right here. I know some of you might have heard of it before and going, oh no, really? This tool is amazing for helping you not only troubleshoot network issues, but to learn networking. I mean, when you look at it, initially it's overwhelming. There's no doubt about it. But when you see just the basics of how to use it, it's like, okay, I think I can really get this. Matter of fact, Wireshark has always, it's always been one of the tools I've had, but I rarely use it. I mean, Wireshark was like, okay, everything's down, last resort, what's going on? Let's get out Wireshark. And then I got a book. I've got it on my bookshelf right here. Pull it off. It's Wireshark Network Analysis by Laura Chappell. It's a big fat book on just this. It's a free utility, and I'm going to flip. Hang on, I'm flipping to the preface here. Table of contents. All right. This is what she said, and this is her preface. Wireshark is and she puts it in all capitals, first responder tool that should be employed immediately when the cries of "the network is slow" or "I think my network is infected" echo through the company halls. And when I read that, I remember reading that years ago, and I go, it's not a first responder tool. This is like the last responder tool. But seriously, that's one of those statements that has just stuck in my head, and over these last few years, I've started using it. It's still not my first responder tool, but I've used it with a lot more immediacy than I have in the past, and it really has saved a lot of time. So I want to get you guys familiar with that right away. So, what are TCP and UDP? They are the primary transport protocols used today. Meaning transport layer of the OSI model. We've got our applications trying to communicate data up here, right? Our Internet Explorer, our what other online games, what other applications do people use nowadays? Instant messengers, all those kind of things are sending their data down here. It reaches the transport layer, and you might remember from the OSI model, this is where it's going to choose the reliability. Is it going to be reliable or unreliable? And then it also assigns the port numbers to start separating the different applications so the operating system can distinctly understand which traffic goes to which application. Now, there are a lot of transport protocols. Again, I'll remind you, the OSI model is a standard of standards. The transport layer is just a shell, but inside of there's all kinds of standards, like TCP is one of them. UDP is another. ICMP is yet another. ESP that's used for VPN connections and things like that. Even you'll start seeing protocols like OSPF and EIGRP. I mean, all of these kind of squeeze right into that green box known as the transport layer. But when we're talking about programs talking across the network, they primarily use one of two protocols. UDP, that's our unreliable version. It's saying, I hope it gets there. Or TCP. That's the I know it got there. That's the reliable version of this. So UDP is the User Datagram Protocol, TCP Transmission Control Protocol. That's what they stand for. And that they combine together with the sub-protocols below. That's why TCP/IP got its name. Is it's not really that's the protocol. It's a suite of protocol. The most common being TCP and IP combined together to make network communication happen. So First off, let's get into UDP. And I talked when we were talking about the OSI model. I got in a little bit of this. Like, why would you want to send something unreliable? Like, I hope it gets there. Well, the first thing to understand is that there is a cost to reliability. In order to say, I know it got there, there's a lot of setup that takes place. The first thing that happens is something known as a three-way handshake. And I'll explain this in just a moment, but essentially the two devices that are talking together have to establish a session between each other and make sure that, okay, we agree to talk, okay, that's good. Okay, so that's a little time right there, a little time to establish that session. Then every single packet that gets sent, or every stream of communication that gets sent, I'm gonna just write something up here. It's my reminder. Every stream of things that get sent between these things have to get an acknowledgement back saying, I got it. Again, more overhead, more delay, where some things just may not need that sort of thing. I want to give you, now I gave you the example back in the OSI model of things that do not need reliable communications, being like voice over IP, where I have an IP phone talking to an IP phone. There's a stream of data going between the two. If something is dropped, it's gone. There's no use in retransmitting it at a later time because it's real-time traffic. Same thing with video over IP. But there's also some other data applications out there that use UDP as well. I want to give you one that you use every single day, and that is DNS. DNS, the domain name service, translates names to IP addresses. Because remember, in the OSI model, at this network layer, we can't squeeze in www.google.com. It deals with IP, the IP protocol. So we have to have some kind of system that takes these friendly names, like I put wireshark.org, I'm going to show that to you in a moment, or cbtnuggets.com, and translates it to what IP address is really there. DNS, at least the client version of it that we use every day, uses UDP. So let's check this out. I'm going to bring up Wireshark. Now, I want to give you a little basics of this program. Wireshark will be flat overwhelming if you just open it up and say, okay, well, let's see what's happening. If you've never done this before, people get scared, they back off, they're like, I don't want to use that again. But let me give you the basics, which will really get you started. And I'll tell you what, if somebody would have sat down with me in my early days of networking and just said, hey, Jeremy, let's just sit down for a second. Let me give you a 5-minute tutorial of this tool that will change your life. And I would have been like, great, thanks. And it just, the fear of it is what held me back for so long. But this is Wireshark 1.82. It is free. You go to wireshark.org and just go to their little download page, and they'll automatically detect your operating system. You can put it on there. It's good. Once you get Wireshark installed, it's just literally a next finish sort of install. This is what pops up. Now, the key icon you want to go to is this list available capture interfaces. And trust me, this is a massive utility. There's a lot to it. I just want to get you the core that will get you started in doing what you need to do. So I click on this, and right here I can see the interfaces that are on my computer. Now I see this Sun, which, if you remember, I had when I went to my control panel and did my network status, looked at my adapter. I had this little VirtualBox host only that's installed by the VirtualBox application. It's a little virtual machine thing. It's developed by Oracle, Sun Oracle. They merged. And so that's what this little adapter is. And I can look, that's why I always go to this view. I'm like, okay, not much happening there. Because if I'm looking here, trying to start, pick one, you can start it from here. But if I don't know which one it is, I want to see where's the traffic happening. So I go, okay, well, it looks like this is where there's some communication happening. So I'm going to click check on this and do start. What I'm going to start seeing is the communication that's going across the network. And this is where a lot of people go, ooh, what's going on? They're not too sure what to do. So right now, this is not much is going on. 29 packets are happening. I can see spanning tree protocol running in the background. Some other, just normal network traffic discovering and communicating with things that are going on in the network. Now, as soon as I open a web browser, and let me move this to the side so you can see it. Let's just go to msn.com. And bam, look at that. I mean, we went from like 29, 30, 50, all the way up. MSN.com came up, and now we're at packet number 1095. All of these things are going on. What just happened? We just had a ton of network communication that comprised 1,200 or 1,280 individual packets. So that's where people go, "Ugh, it's overwhelming. How do I now sift through 1,200 individual packets to really see what's going on?" Well, I'll explain that in just a moment, but let's look at the matter at hand. I want to talk about DNS. DNS resolves names to IP addresses, and I'm going to show you that this is using UDP as its protocol to do it. Now, the first thing that's happening is I'm like, this is just, it's too much. I want to put a filter on. Let me show you one of the handiest filters that you will likely use. It is coming up here. You click in this little filter box, and you'll find, I mean, you can build your own. You can click on this, and it lets you, click through and kind of almost like does a GUI base. Like if I just want to see the UDP traffic or the TCP traffic, I can do that. But I'm going to go in here and just say IP.addr, IP address equals 4.2.2.2. Enter. Now what is that? Actually, you know what? I'm going to even change that further. I'm going to go 4.2.2.3. Enter. Blanks it out completely. What that does is say, only show me the traffic that is going to 4.2.2.3. Getting that so far? So right now, how much traffic is going there? Nothing, because nothing is actually accessing that IP address, so my display is nice and empty. So now I'm going to use DNS to do a little testing. I'm going to open a command prompt in Windows. Start, you can browse to it, accessories, all that, or just type in start run cmd, and bring this to the middle of the screen, and show you first off, when I do ipconfig/all, I have in my list my DNS servers. Shows the primary DNS server my computer is using is 4.2.2.2. The secondary is 4.2.2.3. Now, how did those get there? Well, that was through DHCP. When DHCP gives me an IP address, it can also assign me DNS servers, a default gateway, all that kind of stuff. And so this is the DNS servers I was assigned. Now, since this is the primary, you remember when I was looking at Wireshark, when I set the filter to say 4.2.2.2, oh, hang on, my capture is still going, so it's getting obnoxiously big. But I'm going to stop the capture because we've got enough data. I can see all these little DNS queries, but it's too much. I want to do a little demonstration version. So I'm going to filter this down and just see 4.2.2.3. Now I stopped the capture, so nothing. Oh, I suppose I should start the capture. I was just thinking, so nothing new is coming in. So I'm going to start the capture, and I'm going to say, let's begin this. It's going to ask me, do you want to delete the old capture? Once I click start, I say, hey, do you want to delete the old one? Absolutely. I don't need the old one. So I'm capturing traffic just for 4.2.2.3, or that's the filter of what I'm seeing. I'm going to open my command prompt and show you a handy utility called NSLookup. What this is a utility that allows you to ask questions of DNS. So what it's doing is it's coming up and saying, okay, well, right now you can ask a question of 4.2.2.2. And I would say, okay, well, I want to see who is www.cbtnuggets.com. And 4.2.2 comes back and says, well, actually, they have two IP addresses associated with them, this one and this one. Well, which one am I going to use? Well, the way it works is it's going to do a round robin. Maybe the first time I'm going to use this one, the second time I'm going to use this one, and the name is kind of gives me a little clue right here. It says web balancer. I'm going, okay, so this is some kind of load balancing. Maybe CBT Nuggets has enough traffic that they say I don't want just one web server. I want to kind of balance that between a couple web servers. I mean, we see that again if I type in google.com. I mean, hello Google. They're definitely trying to balance that load because obviously how many people use Google every day. So now what I'm going to do, I was asking questions of 4.2.2.2. I'm going to change it. I'm going to do server equals 4.2.2.3. And so I'm changing the, wait a second, server. I don't know why I put equals in there. Server space 4.2.2.3, which now sets my DNS server to this address. Now watch what happens. I want to do a lookup for what's a small website that wouldn't be. Oh, I have a blog, TechCert. techcert.com. I blog with another guy out there. Comes back and says, aha, techcert.com is this IP address. But now, did you see behind the scenes? It's like, oh, Wireshark is like, I saw it. Something happened right there. So what happens is this guy went out and said, hey, I want to find out what is the IP address for techcert.com.home.local. What the? Like, what? Where did that come from? Oh, I typed in techcert.com, and the only way I would know this is if I was using Wireshark, and it went out and said, well, actually, I want to ask the server, the DNS server, I want to find out who techcert.com.home.local is. Now, why on earth did it do that? Well, when you dig a little bit deeper, let me go back here in my create a second command prompt, and I do an ipconfig/all. One of the things that you can do with DNS is assign computers a default DNS suffix. Where does that go? At the end, right? So that would allow somebody, for instance, if I assign the home.local suffix, it allows somebody to say, I want to ping, maybe the server, and hit enter, and it's going to automatically try and ping server.home.local. Maybe that's my local DNS domain that I have for my house or something like that. So immediately when I tried to ping or look up techcert.com, it came back and was like, well, I'm going to try and look up techcert.com.home.local. Now before we go on, you can even see the reply right here. It's saying, no, there's no such thing. I don't know of a techcert.com.home.local as the DNS server's reply. But let's dig a little bit deeper, because Wireshark actually breaks down communication in the layers of the OSI model. At the very, very, very bottom is, essentially as physical as it can get. It's saying, hey, this is how big the data was. This is, how many bytes were actually sent on the wire. I mean, think of this top one as the physical layer. Then we come right here to the data link layer. Now, what do we expect to see there? MAC addresses. And sure enough, I see that I have the source MAC address. This is my computer right here, and let's prove it. I mean, let's make sure we're doing what's real here. I'll do ipconfig/all. Come up and look again. I look at my MAC address, C8C0, and the last four digits, 6C32. I'm looking over here right there. Now, sure enough, C8C60. So I go, okay, well, I was the source. This is me. And then I went to the destination of, I actually have a little Cisco firewall that runs my location here. And it says, okay, well, I sent it to this MAC address as the destination. Do you see? So, wow, this is really, really good, right? So it starts putting reality to a lot of the discussion we've had up till now on, okay, it's got the MAC addresses in there. Then it says, okay, well, what IP addresses? So layer 1, layer 2, layer 3, IP address, we're actually coming from the source of this, that's my computer. Destination of this, that's who? DNS server. And now we come to the point that started this entire discussion, the UDP protocol. DNS actually uses UDP. Look at it, User Datagram Protocol, UDP. This is layer 1, 2, 3, and 4. It's saying I'm coming from the source port 6353 going to the destination port 53. Okay, stop right there. What that says to me is that my computer contacted this DNS server. I'm .72 is the last octet. This is 4.2.2.3 is that DNS server. And it went to a destination port of UDP, port 53. Oh, my 3's a little odd there. Okay, 53. And it came from a source port of 6353. Now, this is a well-known, I'll put WK, well-known port for DNS, as in all the DNS servers in the world respond on port UDP 53. That's where they expect to receive requests for, and all the computers in the world, by default, will ask questions directed at UDP port 53 of their DNS server. Now, Windows generated a dynamic port. This is not a well-known port at all. This is considered my source port, saying, hey, my question is coming from source port 6353. So when this guy replies back and says, I have no idea what you're talking about, there is no such thing as techcert.home.local, he's actually going to be coming from source of port 53, going to a destination of 60353. But Windows expected that. It expected to get a response back on that source port, and that's actually one of the reasons why DNS uses UDP. This is kind of a stimulus response sort of thing, to where I'm going to say, I want to know who TechCert, I'll just put tk.com, really is. And the DNS server will say, okay, here's your answer. Now, that's all the communication that really goes on between them is, what's this? Here's your answer. What's this? Here's your answer. What's this? Here's your answer. It would just be a waste of time to say, okay, let's build a session between us. Are you okay talking? The other one's like, yes, let's build a and I'm getting into the three-way handshake, building the session. Okay, now I want to know what is the name or IP address of techcert.com. And then send me acknowledgement that you got my question. He's like, okay, got it. I got your question, and here's the answer. It's like, good grief. Why do you need all that overhead just to get the answer of who is techcert.com? So with DNS, it's geared in such a way that you say, hey, who's techcert.com? And if your computer doesn't get an answer back, it's configured to say, well, I hoped it got there, but I don't think it got there because I didn't get an answer back. Let me ask again. And so it'll keep trying to ask because maybe the packet did get dropped somewhere between here and California during that communication. So that's the idea of those port numbers. Now let's go back to Wireshark and look at this communication as a whole. So it's saying, okay, who is techcert.com.home.local? This guy comes back and is like, no such thing. I don't know who that is. Now notice it's asking for an A record. In DNS, that's alias. That's the normal record that people ask for. So it's like, nope, no such thing. So he comes back and it's like, okay, well, let's try this. I would like an AAAA record. He's saying, if I'm looking for this kind of record for techcert.com.home.local, do you know who that is now? And he's like, no, still no such name. So, okay, what's the difference here versus here? Well, this is looking for the IPv4 address of techcert.com.home.local. AAAA record is actually an IPv6 address. So it's saying, okay, that didn't go so well. Maybe he's on TCP IP version 6 because since Windows XP Service Pack 3, all the Windows operating systems have had IPv6 enabled by default, so they're bouncing it. He's like, nope, still no such thing. So then he comes back and he's like, okay, well then, do you have an IP address for techcert.com? How about just techcert.com? He comes back and he goes, actually, I do. And we can expand that out and we can find out, oh, well, here was the query, techcert.com, and here's the answer. Techcert.com came back and this is the IP address that I received. Wow, do you see how this can be really, really handy? Think about it. Let's say we're sitting here and you type in, whatever, you're looking something up and it comes back and it's like no response or request timed out or something like that. Let's just put bob.com. It fills it up. We've got all, tries again bob.com and we get this answer back. But what if it never got the answer back? It just said, request timed out, and you're like, what's going on? Without this tool in the background, you have no idea. This tool is like, oh, it's looking for bob.com.home.local. It's not supposed to do that. Why is it doing that? So that's why Wireshark is really handy. So bring that back around. That's the basics of Wireshark. Again, without this filter, it's going to be just plain overwhelming. But if you can filter it down and start to really look and analyze these packets, you can get quite a bit out of it. So let me clear off the slate and get back to the topic at hand, which is TCP and UDP. TCP, I think we've got it. It's a wing it protocol, right? You kind of chuck the packet, you hope it gets there, and if a response comes back, great. That's how it works. TCP is the I know it got there protocol. The way that it does that is by using initially a three-way handshake to establish the session, and then it uses acknowledgments to make sure that every single packet was received. Now, let me break that down into the fundamentals of how this protocol really works. When I have a computer here, and I say I want to go to, let's just say I want to surf the web and go to cbtnuggets.com. That'll be our example. HTTP is a TCP-based protocol. It says I want to have reliability. Otherwise, web pages might show up, things missing off of them and all that. Now that may happen, but it's not TCP's fault. It's somebody made a bad web page. But TCP makes sure that all of your traffic gets between these two. Now, when these guys start, here's how it works. He will send, when he realizes, okay, I've got the IP address because I looked it up via DNS, the IP address of CBT Nuggets, let's just use some reality here, cbtnuggets.com, there we go, let's just grab this first one, 184.72, so I'll just put 184.72, that's the IP address. He's going to send, the very first packet will be what's called a SYN packet, saying, hey, CBT Nuggets, I would like to start a discussion with you. Are you essentially, let me put it in plain English and then I'll get technical. Are you okay with that? CBT Nuggets says, yes, I am okay with that. SYN ACK. That means I'm sending a synchronization bit, if you will. I'm saying, yes, I would like to start talking to you, which is what these do, and I'm acknowledging yours. I'm saying, I got yours, that's the acknowledgement, and here's mine. So this guy replies back with one final ACK. What do you think that's there for? I got that. I got the SYN message from you. So I'm acknowledging that we're good, and that is what they call a TCP three-way handshake. Every single time you start a session, it's going to do that with the destination. Matter of fact, I am all about Wireshark. Let's prove it to ourselves, right? Let's stop this capture. I'm just going to close this guy. Continue without saving. Okay. Let's clear the filter off, and let's just start a capture. We'll just go to one website, so it should be pretty easy to pull out. Click on Start. I'm going to go to cbtnuggets.com. Enter. Boom. Stop the capture. Got a whole bunch of data, 400 some packets that were sent to generate CBT Nuggets website. Let's go all the way back to the beginning up here where it all happened. Notice that right here, now you might say, well, I don't see any DNS question for who is cbtnuggets.com. I see Wireshark weaseled its way in there, but what's happened is my computer cached the DNS response. It remembers who CBT Nuggets is because I've gone there before. Now those caches will eventually time out, but they'll get there. Now look right here. So we have Google. We're talking to Google, and you might say, well, what's all this stuff happening? Well, whenever you type, I'm using Google Chrome, and I don't know if you've noticed, but when you start typing, you're like, Jeremy, it's starting to, figure out who all the, who is, it's filling in all of this data, so we're able to see, oh, okay, it's filling this in. So every single time Google is going, okay, well, let's find out who Jeremy Chara is, and you click on it. It's kind of weird. I'm looking myself up. But, who is Jeremy Chara? It's constantly going back and forth with Google saying, okay, he typed an I, he typed an O, he typed an A, as it fills out the name. So that's what this little shindig was. Now, here's the meat of it. I come down right here, and I see, okay, this is a TCP-based message, 3 of them to be exact. Notice, SYN, SYN-ACK, ACK. Three-way handshake. SYN, SYN-ACK, ACK. SYN, SYN-ACK, ACK. Now I want to go down a little further because I'm noticing here, notice the source and destination. It came from this server going to this one, right? SYN, SYN-ACK, ACK. And I go down a little bit more, and all of a sudden I see another one. It's like, wait a sec, SYN, SYN-ACK, ACK. So there's more than one. I go down, and all of a sudden I see it looking up all this stuff. It's like I'm looking up some analytics. I'm looking up cloudfront.net, facebook.com. What on earth is going on? And all of a sudden I see all these, okay, SYN with him, SYN with him, SYN with him, SYN with him. All of these are SYNs, and then I start, look at all these SYNs. It's starting all of these sessions with all these different servers, and then they all start coming back. SYN-ACK, 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 SYN-ACK. And then, it's kind of like we get this big merge of ACK, ACK. It's kind of like, what on earth is going on? I just went to CBT Nuggets, and all of a sudden I've got all of these sessions starting. Well, you remember, I think I talked about this in a previous nugget, but this web page is a framework of web pages. When you come here, there's something on here that deals with Facebook. There we go. They've got a little follow us on Facebook link. Maybe that's it. And they've got a little link to Twitter or something that it pulled from Twitter and built this. So this web page is dynamic. It's always changing. It's pulling from all these different servers. So when I come to cbtnuggets.com, I'm actually, these pictures, these videos, everything is pulling from all these different servers. So that's why I see just getting shot into this world of SYN and SYN-ACKs. But let's get back to the base of it all. That's where it started. SYN, SYN-ACK, ACK. So there's got to be more to it than that, right? No, there is. SYN, SYNAC, and ACK introduce something known as sequence numbers. So here's the concept. I wrote it up here so I wouldn't forget, but I didn't forget even though I erased it, called TCP windowing. TCP windowing is the key to network efficiency. So here's the concept of windowing and window sizes. Some people call it sliding windows, if you ever hear that before. Let's say I have a really big file. It's 1.0 gigabytes in size, and I want to send that over to the server. Well, I don't know if you've ever seen this in Windows. If you've ever copied a really big file and you copy across and it pops up that little, copying time estimate window, and it initially starts off and it's like, your time estimate is 2 days, 5 hours. And you're like, what? That's not right. And then Windows like, no, just kidding. Let me back off. Actually, it's going to be 1 day, 3 hours. And you're like, well, what? No. Have you know what I'm talking about? And all of a sudden it's like, no, just kidding. Your time estimate is really 32 minutes. And you're like, okay, that's a little more reasonable. And then, it takes like 30 seconds before it's finally like, okay, really, it's going to take 10 minutes to copy that file. Okay, it's like, okay, what happened between Windows popping up and saying it's 2.5 days to copy this file all the way down to 10 minutes? Well, that's where TCP windowing kicked in and took effect. Essentially, when your computer starts to send that file, this file is actually broken up. The normal packet size for Ethernet is actually 1,500 bytes. 1,500 bytes. That's very small, especially when you're considering I'm sending one gigabyte of data. So little 1,500 byte. That think of this as 1 kilobyte, and you remember there's 1,024K in a megabyte, and there's 1,024 megabytes in a gigabyte. So you're going to send thousands and thousands and thousands of these packets to comprise this. So it sends one packet over there. This guy comes back and is like, oh, okay, great, I got your packet. The very, very first packet of this 1.0 gigabyte file transfer, I got it, ACK. Now, Windows looks at that and is like, wow, okay, if I'm going to send one packet at a time and then sit there and wait for this other side to come back and say, okay, I got it, it's going to take 2.5 days to transmit this file. So the computer goes, okay, well, let's try this. How about instead of sending one packet, I send you 4 packets at a time. So it takes 4 of these 1,500 byte packets of the 1 gigabyte file, sends them over there, and the server comes back and he's like, okay, I got it. I got all 4 of those packets. And the guy, the Windows is like, okay, great, that's better. If I can send 4 packets at a time, then I bet you that I can get this done in like a day and a half, right? It reduces it dramatically because we're being much more efficient. So what's happening over that first 30 seconds or so of that file transfer is it just keeps trying to send more and more and more and more and more and more and more. It's like, okay, I'm going to try and send you 100 packets at a time. Sends them 100 of these 1,500 byte packets. I got all 100 of them. Does that make sense? So that's the concept known as TCP window sizes, or some people call it sliding windows because the window starts small, it slides bigger. But if there's drops, like let's say I send 100 packets and I lost 2 of them, then my computer's going to go, whoa, we're losing data. I've got to pull back and only send a smaller, so the window size slides smaller, and you see the copy time go up. So that is the essence of how computers know how much they're able to send or how much bandwidth they can consume, and they're going to try and consume all of it. Computers are bandwidth hungry monsters. They will try and consume all of the bandwidth that they can on the way to that server until they finally start dropping packets and they go, okay, that's how much I can send at once before I've reached the congestion point of the network. So how did this windowing concept and sending more than one packet at a time fit into this, and where we started with this 3-way handshake? Well, when we do a 3-way handshake, what we're really exchanging is sequence numbers of my packet numbers are going to start here and then keep incrementing as I send you data. So let's look back at Wireshark, get some examples of this. So right here, we've got our 3-way handshake. We've got SYN, SYNAC, ACK. So that's the very first one that we do. So let's break this open. We'll look at the TCP data. and it says, oh, this has a flag, it's a sin, but I want you, and you can, you can dig deep and say, oh, okay, well, it's actually this bit in the, yeah, for now, it's a sin, right? But if you look 3 above that, it says, hey, we're going to be starting from sequence number 0. That's it. So I'm gonna. That's my beginning. That's where my counter begins, essentially. Now this comes back and says, well, here's your sin ACK, right? And what this says is I'm going to be starting from sequence number 2. That's great. And by the way, I'm sending an ACK for 1. What does that mean? So again, let's look. This is my computer saying, hi, sin. I'm going to be starting from sequence number 0. This is them. This is CBT Nuggets replying back saying, okay, I'm going to start from sequence number 0. That's my sin too, but I'm also going to send you an ACK of 1. Well, the way the ACK works is it's always going to be 1 more than your sequence number. So when I said, hey, sin, I'm going to be starting from number 0, he comes back and in his ACK he says, I'm going to acknowledge 1. And what that says to the computer is I've received your 0, and the next sequence that I'm expecting from you is 1. Does that make sense? And then I'm like, oh, and then look at this. And then when I click down here, it goes, okay, great. I'm going to send an ACK back of 1 as well. So what we've done is we say, okay, I started with sequence number 0. Is that good? He goes, absolutely. I'm going to start from sequence number 0, and I'm acknowledging your sequence number 0 by giving you an ACK of 1. Then I come back and I say, okay, ACK of 1, because I don't know why I put a line through that. Because I'm acknowledging your sequence number 0 that you gave me. Now let's start talking. Isn't there a lot? That's a lot. Whoa, that's a lot to just say. Okay, let's now start talking. But then when you start getting into the data, let's see if I can dig into and find some good data transfer here. Got your standard encrypted packets going through there. It's funny because going to CBT Nuggets homepage, there's so much pointers on there that and there's encrypted data, HTTPS, stuff flying all over the place. But right here, I'll just grab this. Right in the middle of this is actually using TLS, which is encrypted data. This is CBT Nuggets sending me some data, saying, and they're saying, hey, this is my sequence number, and I'm acknowledging the last one that you gave me, which was 1639. So you kind of go back and forth. It's just finding the stream. So this guy's saying, okay, we're getting into encryption handshake. So, okay, here we go. I'm sending some data. So I send some data right here, sequence number 348. I move on, sequence number 401. I move on, sequence number 462. So he's sending data, and every time now if I want to see, well, here's the actual data. It's SSL, which is all nice and encrypted. Here's the data that's being sent. It's all encrypted mush going to CBT Nuggets website. But all of that stuff has sequence numbers. So essentially, let me boil it back down on the slide because it's a little less complex than busting out Wireshark. I've got, let's say 3 1500 byte packets to send, right? So let's say I started with sin 0. I send 3 1500 byte packets to the other side. It'll come through. First one will say, "Hey, I'm some data. I'm sequence number 1500." The second one will come through and say, okay, well, I'm sequence number 3000. And third one comes through. You see where this is going? I'm sequence number 4500. The sequence numbers are essentially a mathematical addition of all of the data that's being sent. And that way, when these two get dropped, maybe this one made it through, these two were dropped, all of a sudden this guy goes, whoa, wait a sec. I missed sequence numbers, we'll say 4000 through 6593 or whatever, whatever those sequence numbers are. So he's going to be like, whoa, I did not receive those. He goes, oh, well, let me resend those sequence numbers to you. This is how TCP keeps it all working, is by, again, those acknowledgments coming back. If he received them all, he'll send an acknowledgement for 1 plus whatever the last sequence. So let's say the last sequence number to get in was 4500. He's going to send an acknowledgement for 4501. 1, and then the transmission continues on. It's like right there I took a breath and I took a step back and I'm like, how do you see anything on this screen anymore? It builds on itself, so hopefully you didn't look away throughout, because otherwise it's just a mess of lines going back and forth. But wow, I mean, if take that and put it all together and you are on your way well on your way to becoming a network ninja. Not only understanding how TCP works, the three-way handshake, the acknowledgement back and forth process, but also now starting to look inside of Wireshark and being like, oh, I see the three-way handshake right there. I get it, and then I start seeing that I get referred to all these other servers, because there's their DNS queries, and then I start sessions with all those. That's all these SYN packets. I mean, wow, that's a ton of info that you can say that. I mean, it's rare to find somebody who's able to do that level of knowledge in the network world. I have found that there is a big difference between the amount of time I think it's going to take to talk about something and then the actual amount of time it does. It's all Wireshark. I'm telling you, bringing that tool into this, I mean, the sky is the limit. But boy, do I want to, what I'm going to do is I'm going to break this into two different pieces. So this will be our part one, and then I'll wrap up these other two items in part two. But what did we talk about, and then what do I want you to do with it? We talked about a lot. We talked about UDP and its simplicity, and then we got into TCP, just looking at what is this protocol, how does it communicate in a stable way using sessions with the other side. We saw the TCP three-way handshake. We saw sequence numbers. We saw DNS lookups. We saw Wireshark. I mean, the list goes on. I mean, this was just a packed nugget. So here's what I want you to do with it. I want you to really take the time to start getting a depth behind your knowledge of UDP and TCP. What I want you to do is go download Wireshark. Go to wireshark.org. It's a freebie. Just download that, install it on your laptop or desktop or whatever device that you have. And I want you to go to a simple website. Matter of fact, somebody emailed this to me a long time ago. What was it called? The last page of the internet. That's it. And it's just some guy. This has been around for a long time. Last page, a guy who created a website that just says, "You have reached the last page of the internet. Hope you enjoyed your browsing. Go outside." So beautifully simple web page to where we won't get the confusion behind. I won't say confusion, but the complexity behind going to big websites like CBT Nuggets and seeing 50 different servers pop into our conversation. So grab Wireshark. I want you to capture the DNS lookup, create a filter, find out what your DNS server is, create a filter that allows you to see the DNS lookup, and then one that allows you to see the communication between you and that last page of the internet web server. It'll be nice and simple, so you don't have a ton of stuff to weed through. Also realize that I showed you, a 1/1000th of the possibilities of Wireshark. You can create complex filters, like I could say this and IP address equal, or I could use and or IP address equals such and such. I mean, you can start building numbers where you just capture a certain port number, or I should say filters where you just capture certain port numbers. There's a lot of possibilities. I mean, play around with it. Start tinkering around and really, I would say, add some depth to your knowledge, and then jump into the next nugget where we'll talk about the port numbers and then fit it all together with that end-to-end communication story. I hope this has been informative for you, and I'd like to thank you for viewing.